Hello, my name is Tony Yunshu. I'm a student from Dulwich College, Zhuhai in China. The paper I will be presenting today is titled Based on the Comparisons with Various Types of Transistors to Predict the Trend of Nanotube FETs in the Future. So first part is introduction. Field effect transistor, which short name is FET, is mainly controls the current flow between drain and source, and also gate, which is the three main parts of the FET. When the voltage applied between drain and source, there will be an electric field created so that it allows current and voltage applied to FETs so that it can work in micro speakers or something other smaller electronic devices. And for the different direction of electric field and current, you can divide to N-channel FET and P-channel FET. Let's move to the next part is about the type of FETs. In general, the FETs now can be divided into two types. First is this one called junction FET, and another one is the picture on the right-hand side is called metal oxidized semiconductor FET. Short name is MOS FET. So let's talk about junction FET first. So junction FET is quite different from the bipolar FET because bipolar FET is current control, but JFET is mainly voltage controlled and it has higher efficiency and as well as it's short time to do any reflections about the odor of the electronic device. And it also has two types, N-channel and P-channel. The main difference of them is that in N-channel JFET, it has P-type material, but for P-channel JFET, it has N-type material, which is like in the opposite way. And for MOS FET, for the name we can know it has metal oxidized in, which can show in this graph. We have metal contact, metal gate, and metal contact again for source, gate, and drain. So they use metals as a conductor, which means they have a better way to conduct current and so that the voltage and the electric field will be more stable compared to JFETs. And also the surface of the bulk, which is here and here, in the example actually is made by silicon, which is a good semiconductor metal, so that it has a higher efficiency. And now let's move to some difficulties FET is faced. So first one is about short channel effect. This one is basically happened when like the source and drain are overlap. So let's see this figure. The figure A shows a normal FET, which we can say source is here, gate with drain. But in figure B, we can see this part. So this part. This shows that source and drain, they are overlapped together, which may cause the short channel effect to happen. And what's the effect of the short channel effect? The main effect is like the short channel effect will reduction the voltage applied in the FET, so that maybe the efficiency of FET is reduced and cause electric field between drain and source is not stable. And another difficulties is about gate-induced drain leakage, which is happened like this will causes current to flow from the drain to the source even when the gate voltage is 0. The gate-induced drain leakage is mainly due to a leakage current that enters FET's channel through the gate oxide. Here is a picture, and the left-hand side shows this rectangle part shows where the gate-induced drain leakage happened in a type of TFET, which is like we can definitely show the direction of the normal one is like quite different. And for this graph, we can more clearly find out in purple rectangle shows the ideal ampere and against voltage graph is not quite normal to the usually one, which is in this kind of lines, in these lines. And for the possible solutions of those two, first one, the example is apply step lightly doped drain in a type of FETs. Here is a research provided by university groups. They use different materials on the CNT FET and compare the current and voltage effect on it, and they find out that at voltage is 0.4 volts, the stepwise LDDS CNT FET has the highest efficiency, so that maybe use this kind of new doped drain, we can solve the short channel effects. And for the drain leakage, one invention is about use lightly doped drain, which is quite similar to the first one. And we can use two figures to explain it. So first of all, look at the left one. It shows an NMOS operation FET, which is on state. We can show here is a half rectangle, which is a triangle, but not with a full rectangle. This is called a pitch-off effect, so which is known as GIDL. This will cause the leakage current flows in to the FET. But if we have light Doppler drain between the drain and source and here, like these two light blue square, then the leakage current will be disappear as these two can balance the current flows in and the voltage applied to the both drain and source. And nowadays, with the nanotechnology improved, we have a new type of FET, which is called carbon nanotube FET. This kind of FET is basically use carbon nanotube between source, gate, and drain to conduct some electric carrier by using like some metal layers below it, which in this picture is silicon oxide and silicon substrate. These two can create the electric field, and so that the carbon nanotube can conduct some charge carrier like electrons to move between drain gate source so that the FET can be worked. And the difficulties for CNT FET is mainly, for instance, is contact resistance. So contact resistance happens in CNT FETs quite frequently. This could lead to the reduction of current flowing through, something like low speed of signal, or even device characteristics will be changed. And the main reason causes is because the metal interface and the FET size is too small so that the silicons or other metal contact can't be very stable. And to decrease the impact, one example to use is about chemical doping, and this one is a quite great idea. So what is chemical doping? Basically, it involves use some particular chemicals or elements so that after the CNT's electrical characteristics, and that can lower the contact resistance between the CNT and the metal electrode. It's because chemical doping can change the original metal's characteristics or make some reactions so that make the electric field and voltage supplied more stable and even leads to a higher efficiency way to conductive. In the future, I think CNT FET, the main way is to find more metals or semiconductor metals into carbon nanotube FETs so that it can have a better conductivity so that we can reduce the size of CNT FET, make it smaller and smaller. And on the other hand, this may still cause the cost will be higher. So that means CNT FET may be more expensive. So that make some cheaper materials is also quite important. And that's all of my presentation. Thank you very much.